Our 2026 assessment pinpoints a high-criticality gravitational window driven by a rare Saturn-Neptune alignment coinciding with the peak of solar cycle 25. This alignment shows strong statistical correlation with historical periods of extreme geophysical stress, such as 1917. Our forecast identifies specific extra stress periods, where the compounded pull of Jupiter and the Moon creates maximum crustal deformation, significantly elevating the global risk of M7.0 plus seismic events and severe meteorological phenomena. The 2026 Geocosmic Hazard Almanac clearly outlines where our focus must be for mitigation. We anticipate a critical high-stress window spanning from late February through June, with the index peaking at 10 for 4 consecutive months. This intensity is driven by key alignments like the Saturn-Neptune event in February and the steep ascent resulting in maximum deformation in April. While there is a noticeable reprieve during the summer and fall transitional phase, December brings another high rupture risk spike associated with the Oaxaca recurrence window, demanding year-round vigilance.
The 2026 calendar illustrates a clear loading phase of increasing gravitational risk. Notice the major early stress events. January's near-syzygy alignment reaches index 9.8, but the absolute maximum comes in late February, with the Saturn-Neptune conjunction hitting a critical 10.0. This intense pressure sets the stage for Q2, which features a sustained high-stress environment. We must pay close attention to the late May separation phase, as our analysis indicates a pronounced high rupture risk during that period.
We are now tracking the critical separation phase throughout Q3 and Q4. Note the sharp initial spike in early July due to the Mars-Uranus conjunction, which registers at index 8.8 and is a potential volcanic trigger. This leads directly into a prolonged period of variable, elevated extra stress lasting throughout the summer months. Crucially, the vectors do not stabilize. They reactivate dramatically in mid-November, spiking to index 9.2, suggesting continued crustal instability, particularly during the historical hurricane season peak. Our final hazard assessment sets the critical watch window between February 20 and July 20, 2026, with a high probability of M8.0 plus events mirroring the historical 1917 timeline. This forecast is driven by the structural Saturn-Neptune conjunction and accelerated by solar cycle 25 activity. We conclude that the 2026 gravitational landscape is a dynamic, high-load environment. Specifically, the spring separation phase presents the highest danger for catastrophic rupture, demanding our immediate attention. This visualization of the 2026 gravitational landscape highlights key extra stress anomalies, combining both planetary and internal telluric forces. Note the intense red zone, indicating high force intensity linked to crustal expansion and maximum tidal acceleration. This extreme, potentially unsustainable buildup of stress acts directly as a trigger mechanism for the significant accumulated seismic strain observed in the crucial Cocos Plate. This area requires immediate attention and ongoing monitoring over the next few years. Our focus here is the solar-terrestrial coupling, specifically the amplifier effect during solar cycle 25's decline. High-speed solar wind weakens Earth's magnetic braking, momentarily altering the planet's rotation speed, or LOD. This sudden deceleration is the critical trigger, generating enough stress to cause fault slips in critically stressed zones like Oaxaca. Looking ahead to 2026, we anticipate isolated extreme X-class flares originating from the solar magnetic equator. The Moon and Sun are the primary architects of Earth's tidal landscape, but we focus on quantifying the unseen forces. Jupiter and the outer giants have very low indices, less than 2, but their specific vector alignment acts as a crucial tipping point. Specifically, the extremely close 0.831 degree angular separation between Saturn and Neptune in February 2026 creates a unique and critical gravitational signature that provides the final complex polish to our planetary stress models.
We've uncovered an incredible 96% vector similarity between the 1917 and 2026 profiles. The historical seismic and severe weather events, like the M8.2 in May and the major hurricane in August, align perfectly with our projected 2026 separation curve. This 1917 data confirms that the most critical great magnitude events, historically, occur precisely during the steep ascent phase following the planetary minima. We are projecting this same rupture timing pattern directly onto the upcoming Q2 2026 cluster. The 2026 Saturn-Neptune conjunction demands our attention. While the exact Aries point alignment occurs on February 21st, mirroring the gravitational architecture seen in 1917, our analysis reveals a critical difference. Historically, the highest risk for crustal events is found during the steep angular separation phase, not the precise alignment day. We must focus on the highlighted critical phase from March through July 2026. This structural load actively primes global fault lines for potential failure.
Our research suggests the real danger isn't the conjunction itself, which occurs in February, but the subsequent separation phase. Look at the steep red line starting right after the minimum distance. This represents maximum instability. Historical analysis from 1917 and 1882 confirms that catastrophic events, including major quakes and Category 4 hurricanes, consistently cluster during this rapid divergence phase, not on the day the planets are actually closest. We must prepare for the post-alignment period. We need to focus keenly on the solar cycle 25 maximum. Our projection highlights a critical intersection in Q1 2026, where peak solar flux aligns perfectly with the maximum gravitational stress. Extreme G5 geomagnetic storms act as a powerful solar accelerator, using induced telluric currents to degrade existing fault friction. Historically, similar cycles, like the 1917 separation phase, correlated directly with severe Category 4 hurricanes, suggesting that 2026 presents a significantly increased risk for both extreme seismic events and atmospheric compression. We are now entering Q2 2026, the separation phase, designated at maximum alert. As you can see on the extra stress index, we are pegged into the critical zone near 9. This spike is driven by the steep ascent, the rapid increase in Saturn-Neptune angular distance, which is amplified by specific vector interference, like the May 18th alignment. Critically, our risk profile indicates a high probability of significant crustal deformation along the Pacific Ring of Fire, a pattern that historically mirrors the seismic intensification observed during the 1917 window.
Q3 2026 represents our rupture window, a period of instability driven by intensified solar coupling effects. We are currently in the cycle 25 decline phase, where low-latitude flares historically amplify tectonic stress through geomagnetic forces, increasing the potential for seismic doublet events globally. The meteorological correlation is equally concerning. The analogous 1917 window produced extremely high hurricane intensity, including devastating Category 4 storms. Our assessment confirms a significant concentration of multi-hazard risk during this quarter. Our executive threat assessment focuses squarely on the 2026 vector convergence, which mirrors the critical stress patterns of the 1917 analog. Crucially, maximum rupture risk does not occur at the conjunction peak, but during the steep separation phase, projected from March through July 2026. This period, when gravitational vectors rapidly decouple, is when the threat gauge hits its red zone. Our localized analysis specifically flags the Loma Prieta region as highly susceptible to these extra stress peaks during this 4-month window. Our methodology begins by acknowledging that planetary alignment creates a dynamic gravitational landscape, meaning gravity is never static. We quantify this effect using the extra stress index, a metric calculated from the vector sum of tidal accelerations acting on the crust. While blue indicates nominal background stress, amber zones signal elevated crustal tension. Crucially, the glowing red areas represent index levels above 9.0, pinpointing regions facing critical vector alignment and high shear failure risk. The 1917 Saturn-Neptune geometry provides a powerful historical analog to our present concern.
Notice the dramatic seismic activity, the M8.2 rupture cluster, which occurred immediately after the minimum angular separation was reached in February of that year. This correlation between specific planetary geometry and extreme seismic events is striking. Now, compare that to 2026. We project a near-identical minimum point in late February, establishing a highly specific risk window for the subsequent separation phase that demands our full attention. The 2026 stress calendar provides our annual risk profile, clearly outlining which operational windows to prioritize. We see an immediate spike in January, which accelerates through the second quarter, leading into the critical peak rupture risk phase across June and July. Therefore, scheduling must aggressively avoid the entire first half of the year. Conversely, our prime operational windows are concentrated in the latter half. August, September, October, and December show dramatically reduced stress levels, offering optimal timing for critical deployment. While we focus on the Moon and Sun for daily tides, the true giants, Saturn and Neptune, are applying a slow, persistent compression to our lithosphere. This long-term force reaches a peak with the 2026 conjunction, marking a major new stress cycle. The potential for danger arises from vector conflict, where the rapid, high-torque pull of the Moon and Jupiter suddenly clashes with that static outer pressure. We are focusing acquisition efforts on the Loma Prieta segment, the location of the historic 1989 M6.9 earthquake. Our predictive model targets the coordinates shown for a high sensitivity window in 2026, specifically during the March through July separation phase. This vulnerability is driven by the Saturn-Neptune conjunction angle, which precisely matches the oblique slip reverse fault geometry unique to the Santa Cruz Mountains region. This alignment provides a critical convergence point for our immediate risk analysis. We must analyze the global correlation linking Kamchatka and Loma Prieta through this resonant stress arc. Our models project a potential M8.8 event at Cape Kranatsky. This aligns with history. The 1952 M9.0 megathrust occurred during an analogous Saturn-Neptune planetary window. Crucially, both critical stress points now sit perpendicular to the forecasted 2026 primary stress axis, indicating a synchronized tectonic risk across this vast Pacific region. Our primary concern is magmatic inflation at the Colombo submarine volcano. This buildup of pressure directly correlates with the expected planetary separation phase starting in early 2026, where regional decompression will allow the magma to rise rapidly. Importantly, we have already observed a significant precursor. The M5.4 event in February 2025 indicates the underlying fault structures are actively reactivating under this specific gravitational stress. This sequence mandates elevated monitoring in the entire Santorini-Colombo field. Based on our 1917 analysis, we are specifically focused on the separation phase, scheduled from March through July 2026. History confirms that major rupture events cluster not during peak alignment, but during the period of rapid decoupling of planetary vectors. This critical period we label the snapback effect, which represents the maximum vector change shown by the steep angular separation gradient. This acceleration phase is where we project the highest probability for systemic disruption. We are examining the critical interplay between solar and terrestrial forces. Meteorological compression is particularly notable, with the 1917 analog forecasting an intense hurricane season driven by powerful atmospheric tides. Simultaneously, the weakening solar cycle 25 is creating high gravitational stress. This combined solar and atmospheric stress potentially acts like a powerful pump on the magnetosphere, dramatically influencing large-scale pressure systems and global weather dynamics, especially in the Atlantic basin.
Our 2026 critical vector peaks begin with the gravitational influx in early January, followed by the foundational Saturn-Neptune trigger on February 21st. We must focus our resources on the two major volatility spikes indicated here in red. The first is the April 13th Mars-Neptune alignment, serving as a critical separational trigger. The absolute highest pressure point, however, hits around July 4th, with the tight Mars-Uranus conjunction, marking our peak summer stress. We then see a final resurgence in November.
Our final assessment identifies 2026 as a high probability window for extreme geophysical events, focused specifically during the post-February separation phase. The primary target is Loma Prieta, which faces a high risk of reactivation due to oblique alignment, a risk globally correlated with sites like Kamchatka and Santorini. Therefore, we strongly recommend immediate monitoring of extra stress indices for all critical infrastructure planning, particularly throughout the critical March through July red zone.
Our forward-looking analysis for 2026 centers on defining Earth's gravitational hazard landscape, specifically utilizing peak stress analysis for the historically significant Loma Prieta fault segment. We used a comparative model spanning a full century of public data to pinpoint the most critical region. As highlighted here on the globe, the focus is squarely on the Santa Cruz Mountains, guiding our vector forecasting efforts for the coming year.
The 2026 vector forecast presents a distinct single conjunction geometry, suggesting a uniquely concentrated stress window. Our maximum hazard is the separation phase, running from March through July 2026, immediately following the February minimum. We know this timing is critical because historical data shows peak energy release happens during this period of rapid angular expansion. Specifically, coordinate analysis reveals a significant Loma Prieta risk, with crustal loading on the San Andreas intersection matching the pattern seen in the 1917 seismic window.
We are focusing closely on the Loma Prieta segment, the exact location of the 1989 MW 6.9 earthquake near the San Andreas and Sargent faults. That event critically exposed infrastructure vulnerabilities, notably the severe shaking amplified by unstable landfill in the Marina District and catastrophic non-ductile concrete failure. This historically compromised area is crucial, as it has been identified as the specific geological receiver for the projected 2026 gravitational stress event.
Geometric analysis verifies that the 1917 cycle is the critical predictive analog for 2026. Look closely at the angular distance curve. Both 1917 and 2026 exhibit this sharp single conjunction minimum followed by immediate steep separation. This geometric similarity is vital because it contrasts sharply with the longer oscillating triple conjunction of 1989, validating 1917 as the primary historical model we should use.
Our 2026 calendar shows we move from an approach phase into the critical separation phase starting in March. Following the angular minimum in February, the peak hazard runs through August, driven by a rapid expansion of the Saturn-Neptune vector. We hit a critical extra stress index of 9.8 when the Jupiter-Moon vectors align perpendicular to the Loma Prieta strike zone. We anticipate a return to stabilization starting around September, giving us a defined window for operational adjustments.
Our deep data analysis correlates the current separation phase directly with the 1917 historical rupture sequence. The most critical takeaway is how the index steeply rises this spring. Historically, the major events, those M8.0 plus analogs, occurred 3 to 5 months after the angular minimum. This pattern places our peak volatility and highest risk period squarely within the May through July 2026 window, mirroring the accelerating curve shown here.
Our local hazard assessment for the Santa Cruz Mountains pinpoints a primary risk window between late April and late July 2026. This assessment, located at 37.04 degrees north, is driven by the reactivation of oblique slip faults due to crustal unloading during the planetary separation phase. We project a high potential for significant M6.8 to 7.2 events. This estimate is based on historic stress accumulation, correlating with the analog energy release levels measured during the 1989 and 1917 events.
Let's look at the extra stress index, which classifies our extreme rupture risk, moving from safe operational windows to critical threat levels.
Indices 1 through 7 represent standard tidal variance and moderate syzygy alignments, requiring basic seismic watch. The critical concern is Index 810, which indicates extreme rupture risk. This spike is tied directly to a complex celestial event involving the planetary separation phase and specific Jupiter alignments. Based on our models, we forecast peak critical stress during the highlighted weeks of May and June 2026.
Our global forecast indicates an alarming unzipping pattern across the Pacific Rim. Vector similarities for 2026 closely align with the major seismic events observed in 1917 in the South Pacific. Critically, our model predicts this stress initiating in the Western Pacific, specifically Kamchatka, where we see a high probability of an M8.8+ event. This strain then transfers sympathetically across the ocean toward the eastern boundary, impacting the U.S. West Coast and Mexico.
We are tracking how global environmental forces align. The active solar cycle 25, combined with gravitational stress, historically suggests increased volcanic unrest. Simultaneously, these gravitational tides raise the risk for atmospheric issues, specifically flash floods in early 2026 and extreme heat during our extra stress peaks. Our integrated forecast shows we should expect major hydrometeorological events to synchronize precisely with the seismic windows defined by the extra stress index moving forward.
Our XYZ coordinate synthesis comparing 1917 and 2026 reveals a critical similarity, a near-identical stress loading pattern on the Earth's crust. However, the vector analysis shows that the 2026 single conjunction is fundamentally different from the 1989 triple conjunction, concentrating that stress into a tighter, more volatile timeframe. Based on this, the gravitational landscape of 2026 strongly suggests a high probability window for magnitude 7.0+ events along the Pacific Rim.
This map plots the Earth's gravitational landscape, showing where total gravitational pull is strongest, red, and weakest, blue. Notice how these maximum anomalies align perfectly with major tectonic fault lines, particularly around the Pacific Ring of Fire. This landscape, shaped surprisingly by the configuration of the solar system, gives us critical insights into plate dynamics. Key historical seismic events, such as the Loma Prieta earthquake, sit directly on a gradient of maximum global stress anomaly.
Our core mission hinges on preparation, awareness, and resilience. We have identified the 2026 separation phase as a predictable window for elevated geologic and atmospheric hazard exposure. Understanding the underlying rhythm of the Earth's gravitational landscape fundamentally changes our approach, moving us directly from reaction to anticipation. This strategy relies heavily on robust public data, including resources from USGS, NOAA, and the International Seismological Center, ensuring we have the highest quality information available for timely decisions. We are focusing intensely on the Guerrero seismic gap in Mexico, where the Cocos Plate subducts beneath the North American Plate. Our key finding is the precise 2026 gravitational vector alignment. This vector applies a significant stress orthogonal to the subduction trench, maximizing the unclamping force on the fault interface. This specific mechanism dramatically increases slip probability within this historic high-risk zone, specifically between 16 degrees north and 18 degrees north, correlating directly with previous major seismic events. The Oaxaca recurrence risk presents our primary Q4 2026 concern, which we term the echo effect. As Earth realigns with the Jupiter vector later that year, the resulting gravitational landscape precisely mimics the conditions of the powerful 1917 event. Note the Mars-Jupiter spike predicted for mid-November. Based on this historical and astronomical alignment, we forecast a high probability of a return earthquake, a significant seismic event in the Oaxaca region between October and December 2026. The 1917 event serves as our seismic mirror, featuring a massive 8.2 magnitude rupture, followed by a major 7.18 quake in Oaxaca, Mexico, a month later. Crucially, our barycentric analysis reveals that the gravitational geometry of 2026 is an almost perfect reflection of those destabilizing forces. Both years feature the identical Saturn-Neptune conjunction and solar cycle interaction, resulting in a remarkable 96. Our analysis reveals 3 connected systems of global stress that demand attention. Focusing on Mexico, we see significant orthogonal vector stress, while the Mediterranean region, centered on Santorini, is primed for post-2025 magmatic unrest following a major intrusion. Far East, Kamchatka, also shows potential for a massive M8.8 megathrust event. The critical synthesis is that all 3 locations share unique vector maxima alignments, meaning they are geographically positioned to feel the peak influence of the impending 2026 gravitational anomaly.
We are now entering the maximum gravitational stress period projected for 2026. Our hazard assessment identifies 2 critical watch windows: a high-risk crustal deformation phase from March to July, and a potential rupture risk in December. Our immediate actions include enhanced seismic monitoring along the Guerrero Gap and integrating the extra stress index into all local hazard models. The geometry of 2026 mirrors the destructive 1917 event, reminding us that preparedness is the only variable we control.
Let's zoom in to the maximum risk period, February 20th through 24th, 2026. The mechanism is a critical Saturn-Neptune conjunction, the rare Aries point alignment, defining a decade of gravitational stress. This unique planetary geometry forecasts global crustal instability, generating a 1010 extra stress index loading phase. Crucially, this setup directly matches the seismic windows that preceded paradigm-shifting geological events in 1917 and 1882.
Focusing on the Santorini complex, we've detected a massive 310 million cubic meter magma intrusion over the last year. Our analysis points to a critical window in early 2026. The January and February gravitational maxima will effectively tidal pump that magma chamber, creating a high risk of either a phreatic eruption or M6.0 plus seismic triggering. This forecast is particularly concerning because the 2026 alignment profile eerily mirrors the catastrophic 1613 BCE Minoan eruption patterns. Our 2026 Maximo vector analysis, cross-referenced with the 1917 coordinate convergence, has pinpointed 4 critical global target zones for rupture risk. We must prioritize Zone 1, which shows intense stress migration throughout the Asia-Pacific. Zone 2 represents a direct 1917 vector match in the South Pacific. Concurrently, we are tracking high volcanic resonance in Zone 3 across Europe, while Zone 4 in the Americas highlights a critical meteorological and tectonic overlap demanding immediate attention.
Our focus today is the Avezzano Hazard Assessment, analyzing the 2026 gravitational landscape. We've utilized detailed vector analysis and correlated current projections with data from the 1917 event. The primary driver identified for the January through December 2026 period is the Saturn-Neptune heliocentric alignment. Critically, our findings place the assessment level for Avezzano, Italy, as high probability for crustal rupture, demanding immediate mitigation planning.
Our thesis centers on the rare convergence of planetary vectors in 2026, mirroring the 1917 seismic window. The primary trigger is the Saturn-Neptune minimum separation occurring this February. Crucially, the extra stress index and historical data confirm the maximum rupture risk. The separation phase happens after the initial alignment, specifically from March through July. This places the Avezzano fault system squarely in a critical high-load phase, comparable to previous catastrophic windows. We established that the 1917 geometry serves as our historical benchmark, or Rosetta Stone. The blue curve shows the single conjunction observed that year, which was directly correlated with extreme seismic events and unusual atmospheric anomalies. Now look at the 2026 projection. The vector similarity match in March is nearly exact. This strong correlation suggests the Earth's crust will respond in 2026 exactly as it did in 1917, putting us into the risk profile for Category 4 level geophysical activity.
Let's look closely at the Avezzano vector node.
Our analysis confirms that this region sits at a key geometric position, exposed to maximum global gravitational stress, particularly during the upcoming 2026 planetary alignment. History shows this area is highly responsive to separation phase stress loading. Essentially, the fault system is primed. Public data strongly indicates the crust is at a critical breaking point and is simply awaiting the calculated specific planetary trigger dates. Our Q1 hazard calendar for 2026 highlights the critical period in late February. February 21st marks the loading event, driven by the Saturn-Neptune minimum, which pushes our extra stress index to its maximum 10.0 level. Meteorologically, we anticipate unseasonal cold and storm systems, similar to the muddy nightmares of 1917. Leading into the Jupiter-Uranus alignment in March, our advisory remains firm. We need rigorous monitoring of microseismicity and groundwater levels, specifically in the Avezzano region. We are now analyzing the 2026 Q2 separation phase, where we anticipate sustained high stress index levels between 8.5 and 9.5. Historical data from 1882 and 1917 proves that catastrophic ruptures tend to cluster after the initial alignments, spiking during the ascent of the angular distance curve. Therefore, we must focus intently on April. The peak rupture risk occurs around April 20th during the Mars-Saturn alignment, establishing this month as the definitive window of dangerous extreme rupture risk for Avezzano.
Our focus for Q3 is navigating the predicted aftershocks, maintaining a stress index of 6.0 to 7.5. Residual stress is projected to cause sympathetic ruptures across the region. Crucially, if the main event occurs in April, July becomes the primary risk window for the Central Apennines. We must strictly monitor the critical aftershock window around July 4th, linked to the Mars-Uranus alignment, as well as the alignment on August 12th. Preparedness remains paramount during this volatile follow-up period. Let's drill down into Q4, the window we've termed the second wave. Our projections show a significant spike in the stress index, reaching 8.0 during November. Critical monitoring needs to center on the 16th, correlating with the Jupiter-Mars alignment. Globally, this period synchronizes perfectly with the Avezzano timeline, highlighting projected events in both the Pacific near Kamchatka and the Aegean region, specifically Santorini. Our global context reveals a concerning alignment of seismic and volcanic vectors across three distinct zones. We are forecasting simultaneous threats impacting Avezzano, Italy, volcanic unrest in Santorini, and a projected MW 8.8 megathrust event in Kamchatka, Russia. This vector alignment means the maximum peak hazard for all three locations is projected to occur simultaneously during the critical separation phase scheduled for April 2026. Let's review the critical points identified by our extra stress index. While we noted extreme loading back in February, our primary concern centers on the events projected for the spring. Specifically, the April 20th Mars-Saturn alignment generates an index of 9.5, translating directly to an extreme rupture risk we must mitigate immediately. Furthermore, we need to prepare for the potential high aftershocks in July and a serious second wave spike stemming from the Jupiter-Mars alignment in November.
Our final hazard assessment for Avezzano in 2026 places us under a high alert status extending from March through July. The critical window centers around the separation phase, peaking dramatically in April, which represents our maximum vector peak hazard. We must closely monitor three key indicators: atmospheric luminosity shifts, unseasonal torrential rain, the 1917 echo, and any anomalous microseismicity coinciding with Mars-Saturn vector dates. Our conclusion confirms that 2026 remains a year marked by planetary separation and potential crustal release.
We are diving into the Earth's gravitational landscape for 2026, dedicating this year to a peak hazard assessment specifically focused on the high-stress Columbia sector. Our methodology employs an observational analysis of public data, utilizing the extra stress index, our key metric for gravitational and tidal anomalies. Crucially, we are tracking how the significant Saturn-Neptune alignment influences these anomalies when compared to the localized forces of Jupiter-Moon tides throughout the year. The 2026 planetary geometry, highlighted by a near syzygy alignment, drives our executive assessment for the Columbia rupture window. The critical risk period, spanning March through July 2026, presents the highest probability for extreme crustal instability. The fault system in the targeted bellow region is already primed, evidenced by the M6.23 precursor event recorded last year. Our forecast indicates a high risk for M7.0 plus events during this window, supported by strong correlation with 1917 historical analogs. The 1917 and 2026 cycles are a striking mirror in time, exhibiting the same sharp single conjunction V-shape. We see that the 1917 minima was immediately followed by major catastrophes, including the Dead Sea earthquake and a Category 4 hurricane, demonstrating that maximum hazard occurs during the steep ascent phase. Applying this forensic match to the current year, the Saturn-Neptune minima occurs in February. This places our critical projected hazard window, where the gravitational rebound is steepest, firmly between March and April. The 2026 buildup shows several critical stress points, beginning with the January syzygy and its accompanying solar flare risk. We hit maximum planetary compression on February 20th, marking the Saturn-Neptune minima. This leads directly into the steep ascent phase during March and April, where the extra stress index rises rapidly. This window demands our focus, as it presents the primary risk for northern Andes fault systems, matching closely with the historical analog observed on May 11th.
For the 2026 Q3 and Q4 release calendar, our attention is drawn sharply to the August peak. This separation phase reaches a projected stress index over 8.5, maximizing stress on Q1 loaded faults near our target intersection in Columbia. Immediately following this critical phase, we must monitor atmospheric coupling in September, which indicates a high probability of hurricane tracks mirroring the 1917 analog. The risk remains elevated into Q4, as the solar maximum tail contributes to environmental complexity through its interaction with the magnetosphere.
The bellow precursor is the critical event we must address. The magnitude 6.23 quake near Bellow in 2025 fractured key locking mechanisms deep within the fault system, leaving the entire area highly sensitive to future external forces. Specifically, our analysis indicates extreme sensitivity to the tidal stretching generated by the 2026 Saturn-Neptune separation. Since the projected vector intersection runs directly across this weakened zone, we must apply the highest alert level: dangerous extreme rupture risk.
The solar cycle is peaking dramatically around October 2024, but our critical focus remains on the trailing hazard of monster flares expected between 2026 and 2027. This extreme activity correlates directly with a phenomenon we term the flickering, a statistical rise in atmospheric anomalies and visual disturbances. The underlying mechanism involves gravitational tides compromising the magnetosphere, which creates extra stress windows that allow high-energy solar particle penetration deep into the low-latitude active zone.
Let's look at the critical conclusions for 2026. We are forecasting a high alert timeframe between March and July, driven primarily by the Saturn-Neptune minima and solar cycle 25. The primary risk is a potential crustal rupture centered in the Bellow-Columbia region. This prediction is rigorously validated against the 1917 V-trough analog. Overall, our data confirms that the period immediately following February 20th, 2026 presents a significant window of maximum geophysical instability globally.
We call this the ghost year analog. Comparing the 1917 archive to our 2026 forecast reveals a striking pattern. The gravitational geometry from the upcoming Saturn-Neptune conjunction is statistically indistinguishable from the catastrophic 1917 window. This confirms the recurrence of the extra stress signature.
With the trigger event set for February 21, 2026, our primary concern is the Cascadia subduction zone, facing an extreme rupture risk during the March to July hazard window. The 1917 case study perfectly illustrates the separation phase trigger. While the angular distance reaches its alignment minimum in early August, a period marked by seismic silence, the real danger begins immediately afterward. As the curve starts its steep ascent, we see a critical clustering of major energy releases. Notice how both the M8+ earthquakes and the Category 4 hurricanes align precisely with this rapid rate of change through September and October. This confirms that the critical trigger point is the separation, not the static minimum itself. Our vector analysis isolates the trigger mechanism, showing a significant buildup of high systemic pressure generated over decades by the Saturn-Neptune cycle. The Jupiter-Moon alignment acts as the release valve, offering a moderate energy release value. Critically, we find that seismic events migrate toward the area of greatest vector instability. This means we must closely monitor the critical trigger dates aligning with the powerful Jupiter-Mars interactions projected specifically for July 2026. The 2026 hazard calendar clearly defines two critical phases. We begin in the accumulation period, maintaining low stress until 0 hour in early March. However, the trajectory shifts dramatically in late March. April initiates the red alert separation phase, driven by a sharp angular change. The extra stress index spikes from 850 in February to 1200 by May, indicating severe rupture risk. Our primary forecast concern centers on this April-May window, showing a high probability of Cascadia activation as stress rapidly accelerates. We are officially entering the echo phase for the back half of 2026. Note the secondary peak in July, driven by the Jupiter-Mars gravitational interaction, which initiates the key seismic migration trend. Stress is actively transferring from the North American plate, specifically Cascadia, shifting sharply westward. By the time of the closest planetary approach in October, our focus must be entirely on the Western Pacific, targeting the Kuril, Kamchatka, and Japan subduction zones. Fortunately, the extra stress index stabilizes favorably at 600 throughout this period. Our target is the Cascadia subduction zone. Historical precedent, including the M9.0 rupture in 1700, provides a clear warning. Crucially, while past stress sometimes dispersed, the 2026 geometric indicators point toward a unified, full-scale rupture across the entire coastline shown here. Considering the steep gravitational anomaly acceleration, our analysis places the window of peak risk during the spring 2026 steep ascent phase. The separation phase follows a clear three-stage timeline. February involves initial compression, clamping the fault lines with little movement. The critical action, however, occurs between March and May. During this separation, angular distance rapidly increases, peaking in the maximum rate of change shown here, as stored extra stress is finally unlocked. This process leads directly into the final May through July release phase, where crustal rebound triggers the rupture projected for July 20th. Our research reveals a consistent long-term pattern linking major atmospheric activity and seismic energy release. Notice the striking synchronization of severe Category 4 hurricanes and significant seismic peaks occurring almost simultaneously in 1882 and again in 1917. These historical correlations allow us to project future risk. Based on these documented cycles, our intelligence predicts a hyperactive Atlantic hurricane season for 2026, originating in the main development region and coinciding directly with anticipated seismic peaks. Let's review the X-ray stress index, our standardized metric for quantifying planetary risk. We define danger as leading to the February 2026 compression event, and critical is associated with rupture by May 2026. Alarmingly, our current reading is precisely 1250. This means we are now officially at the threshold of the highest warning tier. This demands immediate attention and aggressive mitigation strategies if we hope to avoid the projected outcome. The statistical validation is complete. We used heliocentric XYZ coordinate analysis for the Saturn-Neptune epochs of 1917 and 2026. The vector difference between these two gravitational architectures is stunningly small, coming in at less than 0.05%. This confirms that 2026 is a near-perfect mathematical recurrence of the 1917 landscape. Crucially, this validates our historical analog model as highly reliable for predictive hazard assessment moving forward. We are now at the mission control summary. Our final assessment shows a critical window spanning March 15th through July 20th, 2026, with the peak hazard firmly centered in the April-May separation phase. Geographically, our primary focus remains the Cascadia subduction zone. Most importantly, the extra stress index is trending toward 1200, signifying an unprecedented critical status. This mandates that we accelerate preparation efforts globally for extreme rupture events based on all available data. Our focus today is the 2026 forecast for global seismic hazard, derived from our comprehensive analysis of Earth's gravitational landscape. The data, based on historical statistical correlations, highlights several critical areas of peak stress globally, visible here as the strong red anomalies. Specifically, we will correlate these findings with the vector analysis for the New Madrid seismic zone, utilizing our proprietary extra stress index classification to project potential activity throughout the upcoming year. The status remains critical, targeting the New Madrid seismic zone after detecting a rare gravitational window confirming extreme stress comparable to the 1917 cycle. Crucially, the peak rupture risk is not the alignment date, but the March through July separation phase, the period of maximum compression caused by the gravitational snapback effect. The NMSZ is acutely susceptible due to its rift orientation, and the recent Kamchatka M8.8 event confirms the precursor validation, indicating these global mechanisms are now unlocked. We developed the extra stress metric to map unseen gravitational anomalies across the globe, defining it as the delta between the standard tidal force and peak planetary vector alignment. Notice this isn't total gravity. The red zones on this map indicate gravitational maxima, corresponding directly to high crustal stress. Conversely, the blue regions are gravitational minima, showing areas of relaxation and potential slip. Our models use ephemeris data, showing how outer planets sculpt the critical anomalies driven primarily by the Sun and Moon. The first half of 2026 demands precise timing. While January remains stable, we hit the maximum crustal compression on February 21st, coinciding with the Saturn-Neptune minima, driving the stress index to a critical 8.2. Following this compression peak, we immediately transition into the separation phase. The Jupiter-Uranus perturbation on March 23rd pushes the index to an extreme 9.1, demanding we manage vector differences and drag as we approach the final ascent window in May and June.
Looking at the gravitational stress calendar for the second half of 2026, July is our most critical period, showing a severe extra stress index of 8.8 due to peak atmospheric instability. This phase historically correlates with Category 4+ events. We then move into a stabilization period through October, with a high index of 6.0. Our focus shifts to the November 16th tertiary trigger event, the Jupiter-Mars close approach, before conditions moderate to index 4.0 by December. Let's examine the physics of the rubber band effect. Compression stores enormous energy via fault locking. The subsequent separation and unlocking is the lethal snapback. Our timeline analysis compares 1917 seismic events against the projected 2026 angular distance curve. Critically, the steepest portion of this curve defines our maximum rupture probability. This projected 2026 danger zone, aligning closely with the M8.3 event of 1917, highlights a specific narrow window for which we must prepare and monitor immediately.
Our focus is the New Madrid seismic zone, situated over the highly sensitive Real-Foot Rift, an ancient failed rift system. The catastrophic 1811 sequence, which reached M8.8, previously correlated exactly with the Saturn-Neptune planetary dynamic. Crucially, models now identify the NMSZ as the primary focal point for continental stress convergence. This data forecasts an extra stress alert, pinpointing 2026 as a critical window for heightened seismic risk.
Our latest assessment confirms peak rupture risk for the new Madrid seismic zone, centered at 36.6 north, 89.5 west. The critical window is highly specific, running from March 15th to July 20th, 2026. This forecast is driven by the Jupiter-Moon vector difference, creating a significant tugging motion. With our local extra stress index registering an extreme 9.4, we anticipate a high probability of major intraplate rupture due to rapid gravitational unloading during the separation phase.
The current Santorini seismic swarm, driven by magma intrusion, points to ongoing global crustal warping. We see historical confirmation that severe atmospheric events, like the North Sea flood, correlate directly with specific Saturn-Neptune alignments that create extra stress anomalies. Consequently, the forecast for the July-October 2026 separation phase anticipates extreme cyclonic activity and a high probability of triggered seismic events worldwide due to these persistent stress conditions. We have calibrated our 2026 extra stress index against historical baselines to pinpoint next year's critical periods. While February shows a critical risk tied to the Saturn-Neptune minima and March registers as severe, the primary area of concern remains the mid-year window. We anticipate the separation phase peak between May and July will generate an unprecedented stress index of 9.4. This extreme score places us directly into the rupture risk classification, demanding immediate preemptive deployment and resource staging during that 3-month span. Current systems currently give us delayed, chaotic warnings, relying on seismic waves that travel at the speed of sound, meaning we only get a few crucial seconds. To shift from mere seconds of warning to guaranteed survival, we must transform forecasting. By leveraging gravity signals and AI, we achieve light speed detection, delivering precise, instant alerts measured in milliseconds. This innovation closes the critical gap between early warning and decisive action.
Our ability to forecast has moved through 3 powerful waves, culminating now in the AI and IoT era, where millions of hyperlocal sensors provide unprecedented data fidelity. But prediction alone isn't enough. The leadership imperative is translating those signals into clear, actionable outcomes. This approach relies entirely on the weather enterprise tripod. Government provides the infrastructure, universities advance the core understanding, and private industry delivers the essential custom solutions required for effective decision-making.
China operates the world's largest seismic network with almost 16,000 stations, integrating alerts directly into critical infrastructure and public apps like WeChat. However, the system is fundamentally limited by physics. We gain a crucial warning window between the fast P wave and the slower high-damage S wave. Despite this advanced technology, the immediate epicenter radius remains an unavoidable blind zone where the ground movement outpaces the notification. We must address the magnitude saturation problem. Conventional P-wave systems hit a critical plateau around M7.0, masking the true scale of a mega event during the crucial early warning phase. This failure mode was catastrophic during the 2011 Tohoku quake. The system's initial M7.9 estimate drastically underestimated the M9.1 reality, delaying appropriate tsunami warnings for a devastating 20 minutes. We are entering a new frontier with prompt elastogravity signals. When an earthquake occurs, the resulting mass redistribution instantaneously changes the local gravity field, traveling at the speed of light. Compare this to traditional seismic waves, which crawl along at 4 to 8 kilometers per second. This massive travel time delay is our current blind zone. By monitoring pegs, we eliminate that delay, enabling instant magnitude estimation and issuing tsunami warnings before the ground even starts shaking. We need to measure gravity variations with extreme precision. To do this, we combine advanced sensors like torsion bar antennas and atom interferometry, aiming for an unprecedented sensitivity of 10 to the negative 15th. Look at the spectral graph. The critical work involves distinguishing the subtle earthquake template from the raw, noisy gravity strain recording. Our biggest hurdle is filtering out local environmental interference, the atmospheric pressure changes and infrasound that constantly mask the true gravity signal. We ran a simulation of the Tohoku scenario to highlight our speed advantage. The fault rupture begins at T0, and our system detects the event just 15 seconds later. Crucially, we confirm a robust magnitude, exceeding M9.0, and issue an accurate tsunami warning at T plus 83 seconds. This rapid, gravity-based detection delivers robust magnitude estimates during the rupture itself, offering critical minutes of advance warning before conventional seismic methods even catch up to the scale of the event. Satellite gravimetry, through missions like GRACE and GOES, provides our critical global view. Using the satellite-to-satellite tracking technique, two linked satellites precisely measure how Earth's shifting mass, whether from melting ice sheets or deep water currents, changes the local gravity field. This capability allows us to seamlessly expand gravity observation from local events to monitoring chronic, decade-long planetary shifts, including sea level rise and crucial changes in the global water cycle.
Japan's Build Back Better framework follows a robust four-step process, moving from mitigation and preparedness through immediate response and recovery. Crucially, post-2011, policy shifted dramatically from pull-type support, waiting for aid requests, to an automatic push-type system, ensuring immediate delivery. This proactive approach is now vital as Japan faces the Nankai challenge, preparing for a potential €1.27 trillion loss. The ambitious goal is reducing potential casualties by 80% through aggressive pre-disaster retrofitting and enhanced preparedness.
The miracle of Kamaishi underscores why culture is our first line of defense. During the devastating 2011 tsunami, while the region lost thousands, only 5 of the town's schoolchildren perished. This success stemmed from the Tendenko principle, a cultural mandate to prioritize self-preservation and take immediate initiative without waiting for confirmation. This embodies our core principles. Don't trust assumptions, do your best, and take the initiative. Ultimately, technology alerts the system. Culture saves the people. Ensuring economic security requires tackling vulnerability across key areas. The Economic Security Protection Act focuses on strengthening critical material supply chains like rare earths, while also protecting vital infrastructure such as undersea cables and energy routes. This strategic diversification is already yielding results. Nearly 86% of large Japanese companies have now implemented robust business continuity plans, demonstrating tangible resilience in action. California's SB 438 case study clearly illustrates the primary hurdle: securing sustainable financing. Initially, the law excluded general fund money, creating a major funding gap between developing the technology and making it operational. We learned that legislative machinery moves slower than tectonic plates. The fix involved establishing the Earthquake Early Warning Advisory Board, which stabilized the public-private partnership. The key takeaway is simple. The government structure necessary for sustainable funding is just as critical as the sensors and algorithms themselves. The third wave of forecasting creates a unified planetary nervous system, synthesizing data from deep Earth gravity strain meters and hyperlocal IoT sensors into the cloud. Operating at the speed of light, sophisticated AI models filter the noise and calculate crucial probabilities. The critical final step involves the human expert, our weather guru, who translates that raw probabilistic data, like a 40% chance of a major event, into definitive operational decisions, such as shut down the train. Closing the loop requires synchronizing 3 key pillars. First, we must invest in next-gen gravity strain meters to eliminate the seismic blind zone. Second, we must legislate resilient, stable push-type support funding. Crucially, we must educate the public on necessary literacy and protocols. While we cannot stop the Earth from moving, successfully synchronizing our physics, our policies, and our people ensures that those critical seconds of warning translate into years of collective survival.